we're going to start focusing on forces. And when we talk about forces, this falls into the big category of what's called dynamics. And so up to this point, we've studied kinematics. And kinematics tell us how things move. How fast, how far, how long did it take? Those are the types of questions we've been answering. And so now we're going to start kind of switch gears and start talking about why do things move, right? And that has to deal with forces. So the kind of two categories things fall into is how things move or why things move. And so we're really getting into the dynamics side, and that has to deal with things called forces. So does anyone have a basic definition of what a force is? Force is always given with a capital F, and then we label our forces within that. But do you know what the general definition is for a force? A force really is defined by any sort of push or pull on an object. Okay, so any single kind of push or pull that's exerted on an object is considered a force. Can you think of any types of forces that you're already familiar with? Anytime I pull or push something, that's considered a force, right? Moving this table, pulling it back, all considered forces, okay? We're going to go through a few different types of forces, but there's one specific one that maybe you don't even think about as being a force, okay? What is it that causes things to fall? Gravity. And gravity, believe it or not, is considered a force, right? There is a gravitational force that happens between any two objects. And most often, the gravitational force that we think of is really the gravitational force between the Earth and whatever object we're looking at, whether that's us, whether that's the table, whether it's a ball that's falling, right? The Earth is pulling things towards it, right? With a much greater magnitude than anything else, because nothing has a greater mass than the Earth itself. Right? So we're going to look at that and kind of study that later. But the force of gravity happens between any two objects. But most often we're talking about between the Earth and the object. Okay? So give me some examples of how do forces affect the motion. So how can forces change the motion of an object? Okay? They can make objects speed up by being pushed. They can make objects slow down. They can make objects change direction. So forces have a lot of influence over how objects move, right? How far, how fast, how long. Those types of questions can also be answered, but now we are going to know why they're doing what they're doing. So there's only a couple vocabulary terms that I even really familiarize you with for this chapter, and these are the two right here. So the system is the object we're examining, or the object that we're manipulating. So we're dropping, we're pushing, we're whatever we're doing with that object, but that's called the system. And then the agent is the thing that's exerting the force. Okay, the thing that's causing the force. So if I lift my pencil right here, the pencil, is it the system or the agent? It's the system, and what's the agent? Me, yeah, or my hand, right? I'm exerting that force, which causes my system to move, okay? Not vocabulary terms that I think are really, really important, but you're going to see them used. So I just want you to be familiar with them, okay? So, sorry, did I skip something there? Okay. We're going to talk about Newton's 3 laws. Newton has 3 big laws of motion, okay? Do we know or have any idea about what the first one is called? Newton's law of inertia. Have you heard that one? The law of inertia. And the law of inertia has a fancy definition and then kind of a tagline definition. Okay, so the law of inertia says every body continues in its state of rest or in its uniform speed in a straight line unless acted on by a non-zero force. So that's the fancy definition, right? The tagline or the easy definition means this: bodies at rest tend to stay at rest, and bodies in motion stay in motion. Have you heard that tagline before? Okay, so that's what Newton, his law about inertia says that, because if we are talking about a perfect physics world, right, we're ignoring friction, we're ignoring air resistance, we're ignoring any outside bodies. If I were to set a ball into motion, right, if I were to push the ball and it would start rolling, in a perfect physics world, that ball would keep rolling, in that direction at that speed forever, unless something stopped it, right? Unless it ran into a wall or unless it was pushed by something, right? It would continue in motion at uniform speed in a straight line, right? Unless it was acted on by an outside force. So that's what the law of inertia says. An object at rest stays at rest. An object in motion would stay in motion. So what inertia means, right? Inertia is this concept that basically is an object's tendency to resist change. So if it has a lot of inertia, that means it really does not want to change its motion. If it's at rest, it's hard to get moving. And if it's in motion, it's hard to get stopped. So what objects do you think have a lot of inertia? Really heavy objects or really light objects? Heavy, right? If I have a really heavy box, a heavy crate, and it's at rest, will a little push get it going? No, right? I have to exert a lot of force. Or just like the same thing, if you think about a boulder rolling down a hill, is it easy to get stopped? No, right? It's got a lot of motion. It's got a lot of inertia. It's already in motion and it does not want to stop, okay? So the inertia is essentially the tendency to resist change. So that's Newton's first law. We're going to talk about forces a little bit, then we'll move on to his next one. But that's his kind of most, I would say, his most famous one. All right, so let's talk about forces. Forces are vector quantities, which means they must have both a magnitude and a direction. Has to have a magnitude and a direction. Right? What are some other examples of vector quantities that we've studied so far? I can think of 3 big ones. The next in our vector quantities is forces. They have to have a magnitude of direction. We also represent them with an arrow. Okay, we draw our arrow in the direction of the motion, and we attempt to draw them to scale. Okay, and so remember, when we talk about drawing to scale, we're kind of talking about a proportional scale. So if I say he applies a force of 10 newtons, sorry, that's the unit. I'll talk about that here in a second, and then a force of 3 newtons, did I draw those to scale? No, right? They need to be appropriately sized. So if that's 10, 3 would need to be about that, right? We need to draw them to a proportional scale. So we need to draw them approximately the appropriate size, okay? The unit for any type of a force is called a Newton, and it is abbreviated with a capital N. So if you see something like this, 10 N, that doesn't mean 10 north, it means 10 newtons. Okay, and so a Newton, 1 Newton is equal to 1 kilogram times meter per second squared. That's how the unit came about, right? It's mass times acceleration. But rather than have to write out that unit every single time, we kind of abbreviate it and called it a Newton. Okay, so it means that in order to solve for forces, my mass has to be in kilograms and my acceleration has to be meters per second squared. Otherwise, it won't work. Okay, so forces have to be, when we do math to solve for forces, it has to be mass in kilograms, acceleration in meters per second squared. Okay, but the unit is newtons, so it's always going to be a capital N. Okay. So any type of force you see with an N is a force, okay? I'm going to introduce you to the 2 categories of forces, okay? The first which is called a contact force. What would you assume that means? A contact force has to be what? It has to make contact with the object. So it is any sort of push, a pull, holding on to something, any of those objects that come in contact, the system comes in contact with the agent is considered a contact force. Okay? A lot of times I give these just kind of a nickname of an applied force. Do you know what applied means? Right? An applied force means that I applied a push on the textbook. That's all that I mean. So I kind of nickname these category of forces applied forces. Right? When I push my object, I'm not going to label it as force push. I might just label it as force A for force applied or force APP or something like that. So when we label our forces, we can kind of give them nicknames like that. Second main category of forces are called field forces. Any guesses as to what that might mean?
Gravitational pull, like a field.
Yep. These are forces that can be exerted without contacting the object. They don't have to come in direct contact to the object. So gravitational force is one, and there's one other kind of big force that falls into this category. Any ideas about what that might be? What's another way we can get something to move without actually touching it? A magnet. Good. Magnetism is the other main field force. Very good. So gravity works without coming in contact with our object, and so does magnetism, right? Okay, any questions so far about just kind of the overview of what forces are? All right, so now we're going to get into a little bit more of the math part of it and the diagram part of it. How do we represent forces? How do we draw them? Things like that. So we're going to start with what's called the net force. Do you know what net means? What does net mean? If I talk about net profit, net gain, net worth, it means overall. It means the overall of that object. And so it essentially means the sum of all of the forces acting on an object. Okay, the sum of all of our forces. And I want you to make a little extra note here. We are still, when we look at net forces, we still have to think about X and Y separately. Okay, so we're still going to keep X and Y separate. Oops. When we solve for net force, we're still going to keep our X and our Y forces separate. So if I'm talking about the net force of an object that has a force pulling it up and a force pulling it to the right, I've got to analyze those separately, right? My object might move in that direction, right? I would agree with that. But if we're going to calculate the net force of something, I would have a net vertical force and a net horizontal force there. Okay, so we're gonna analyze those here in a while, but I wouldn't be able to put those together into an equation. Okay, I'm gonna keep my x's and my y's separate. Okay. All right. There are a couple of situations in which our object would have a net force of 0. Okay, so being at equilibrium means that our net force, or F net, is equal to 0. Okay, when I write F net, that's just a way that I label my forces. That subscript F net means that I'm talking about the net force. Do we feel okay about that, right? Capital F stands for force, and then I'm going to label what kind of force it is by using a subscript like that. Tell what kind of force it is. So when we're looking at this, an object can be at equilibrium. Okay, and when we talk about equilibrium, that means our net force is equal to 0. It's not move. It doesn't have any acceleration. Okay, when it's at equilibrium, it means that the object is either at rest or that it's moving at constant velocity. Those are the two situations in which our net force could be 0. Okay, net force could equal 0 when my object is at rest or when it's moving at a constant velocity. Those are really the two scenarios in which my net force could be equal to 0. Okay? So equilibrium is the same as saying my net force is equal to 0. Okay? And that happens in two scenarios, when my object is at rest and when it is moving at constant velocity. Okay, remember, we could be talking about at rest vertically, right? Or at rest horizontally, or whatever we're looking at here, but we can see two different scenarios. Okay? All right, we're going to look at how do we represent a force, right? And how do we draw them? We already said we draw them with arrows, but we're going to draw a specific type of diagram called a free body diagram. Okay? A free body diagram. So a free body diagram is basically a force model. We identify every place that the object touches the external world, or every force that's acting on it. We draw them as vectors in the direction of the force stemming from the object. So let me just show you what's happening over here in this diagram. We see the system, which is the book, okay? And what does it look like is happening to the book? It's being pushed, right? So our object is being pushed to the right. So over here we have what's called a free body diagram, okay? Our object just gets represented with a dot. There's no need for us to draw a fancy picture of the object, right? A dot is sufficient. Then the object, it says we're pushing it to the right. Now it's important, let me draw another diagram down here. It's important that our forces don't look like this. Just because it's pushing to the right, we don't push them into the object, right? We're gonna draw our forces that go outward from our system, okay? So our object is being pushed to the right. It doesn't have any indicator on here that there's any friction happening, right? If there was friction, it would oppose the motion and it would go in the opposite direction. But there's nothing drawn here, so we don't include friction. Okay, what do you think this downward force right here means? Force of the Earth's mass on the book. It means gravity, right? I would never, ever ask you to write out a subscript like that. That's ridiculous. Okay, that is way too much. When we talk about gravity, which this force is, we label it as Fg. That's the force of gravity, right? The force of gravity. It is the gravitational pull of the object from the Earth. And it always points straight down. Now, does gravity ever stop working? No. So you're always going to have a gravitational force. Now, in this example, is gravity affecting the movement of the book? No, because it's only moving horizontally. But if gravity was the only vertical force acting, my book would start to fall. But it doesn't. So what's keeping the book from falling here? The table. Okay, so whenever there is an object that's sitting on a surface, whether the surface is a table, whether the surface is the ground, right? It makes no difference what the surface is, but that surface exerts a force upward on the object. Okay, so the force of the table on the book, we're going to relabel that to be called the normal force. So Fn is called the normal force. And we're going to explore that a little bit more here later. But Fn is the normal force, and it is exerted perpendicular to any surface that we're sitting on. Okay, perpendicular to the surface. So in this case, my object is resting horizontally, so my normal force is going straight up, right? That is perpendicular to the surface. Okay? Now, in this system, I want you to tell me this. Is my book moving vertically at all? No, it's at rest vertically, which has to mean that those two forces are congruent, right? This system vertically is at rest. Do we feel okay about that? So my net vertical force here would be 0. My normal force and my gravitational force would have to be equal to one another if my object is not moving up and down, which it isn't, okay? So at rest, vertically here would be true, but it is not at rest horizontally, right? It would be in motion horizontally. Okay, so do we kind of feel okay analyzing what that table looks like? Or that, the diagram? Mm-hmm. Okay. Let's see here. Label each force. Vector should be drawn to scale. Okay, we already talked about that. Arrows are going to go away from the system. So let's draw some free body diagrams here, just practicing the diagram itself. Okay, this says, draw the free body diagram of an object accelerating in the rightward direction. Accelerating in the rightward direction. So we have to figure out, what does that mean? Okay, it says to include frictional forces. So we're just going to draw our object with a dot. We have to assume that gravity is always present, right? So we're going to draw that downward force. And what do we label? How do we label the gravitational force? Fg. Okay, and it's got to be on a surface, right? My object has to be on a surface, so there's got to be a force that's exerted upward from the surface. And what did we say we're going to call that one? The normal, or Fn, right? The normal force. So those are forces that are kind of just givens, right? It's got to be on a surface, and gravity never stops working. So those we aren't even concerned about in the problem. But now it asks, it's accelerating in the rightward direction. So we know we've got to have some force that's being applied to make it move to the right, right? So I just call that force applied. I don't know if it was a push. I don't know if it was a pull. I don't know what made it go, but I know we had to apply a force of some kind. Would we agree with that? Okay, so now I still have to include frictional forces. Which direction would my frictional force go? It's going to oppose the motion. So if my object is moving to the right, my friction has to go in the opposite direction. Now, here's my question. Would my frictional force be equal to my applied force here? No. And why not? This one right here. It's accelerating in the rightward direction, which means my applied force is enough to overcome friction and to keep it moving faster. If friction and applied were equal to each other, it would be moving at constant speed. Or it wouldn't be moving at all, right? If my net force was 0, that happens at constant speed or at rest. But it's accelerating, so that means my frictional force just needs to be shorter than my applied force. And I don't know the scale because it didn't give me any numbers, right? But I can show here that those are not equal to one another. And that tells me that my object is accelerating to the right. It's not only moving to the right, it's getting faster as it moves to the right. Okay, do we feel okay about how that's drawn? Right, the word accelerating is really important when we look at how our vectors are drawn. Accelerating means our net force in the horizontal direction here would not be 0. Right, we would have an object that's accelerating. Okay, let's try this one. A car is coasting in the leftward direction and slowing down. Okay, a car is coasting in the leftward direction and slowing down. So what are the things we have to draw before we even start thinking about left or right? Yep, we've got to draw always gravity, and our car has to be on the surface, right? It's got to be on the ground. So we're going to have the normal force there as well. Okay, is my car moving vertically at all? No, so I would have to know that those two forces are congruent. So do you know what those little lines mean? Have you seen those in math? Right, those are congruency lines. So it shows me that the forces are equal. That's not something you have to draw. I just think it's helpful for me to remember, like, oh, those two forces are equal. Okay. Now, tell me what happens when you coast in your car. Are you applying the gas or the brake?
No.
You're not applying anything. Okay, so let's vision this. I'm moving to the left, but I'm not applying the gas or the brake. So what is causing me to slow down? Friction. Okay, so where would my frictional force have to be going? To the left or to the right? To the right, because I'm moving to the left, right? My car is moving to the left this time. And so my frictional force would have to be to the right. And that would be my diagram right there. Okay, how do we feel about that? Okay, we've got to take into account all of the forces that are acting. But that's what it would look like. Okay, what if my system had said we're slowing down in the leftward direction due to the brake pedal and friction? So I would have to include force of friction and the force of my brake. You know what I'm saying? I could add those additional forces. I just add them right onto the end there. Okay, I don't want you to do that for this example because that's not what it says. But if it had told me I've got multiple forces slowing me down, I would just keep adding them right onto that same exact part of that. Okay? All right, let's get to how do we calculate net force. We drew net force. We talked about what it means, but how do we calculate the net force? Okay, so these are some basic free body diagrams. These don't include gravity drawn on them. These are just left and right, almost like a tug of war situation. Okay, so in this first diagram, we've got 100 newtons that are going to the right and 100 newtons that are going to the left. Does it make sense that our net force is equal to 0? Right? We've got 100 positive, 100 negative. Now, I'm going to give you a really simple template for how do we calculate the net force. The net force we calculate by taking positive forces minus negative forces. Okay, so you can think about it as rightward forces. F net equals rightward forces minus leftward forces, if you want to think about it that way. Okay, we actually do that calculation, and in your head, you did that calculation really quickly, right? You said 100 minus 100 has to equal 0, right? You did that calculation without even thinking, but that's the template that you used, right? To the right are positive forces, and to the left are negative forces. So if I'm going to take all of my rightward forces, add them together, subtract out all of my leftward forces, that would give me my net force. I can do the same thing for up and down as well. Okay, so if I was talking about my net force in the vertical direction, I would take upward forces minus downward forces. Okay, all I'm doing is taking my positives and subtracting out my negatives. What I cannot do is mix and match horizontal and vertical. I could not take a rightward force minus a downward force. That wouldn't work, right? I've got to keep my x's and y y's separate. Okay, are we on the same page with that? Okay, so even though this template is really simple, we're going to use this a lot. Okay, so if I were going to calculate the net force in this system, I've got 100 newtons to the right, another 100 newtons to the right. So what would my net force be? 200 newtons, right? I would probably draw this one like this. 100, and then again, 100, right? And so it ends up being 200 newtons to the right. Okay, they are in the same direction, so we add them. In this diagram, are there any forces that go to the left? Are there any negative forces? No, so I take all the rightward forces and I add them together. I subtract out all of the negatives. What about this one? My net force equation here would say my rightward forces, 100, minus my leftward forces, which is 200, and that gives me a value of negative 100 newtons, or you would say 100 newtons to the left. All right, does that make sense how we set that into that template? Rightward forces minus leftward forces. Okay, so you either tell the direction with the arrow or you put the plus minus sign. Okay, that's version 1 of how we can set up and solve for the net force. Okay, I think that could be helpful for you to put it on your equation sheet. You don't necessarily have to. Okay, here's what I would, if you want to write this on your equation sheet, here's what I would write. Okay, I would say F net is equal to rightward forces minus leftward, and F net is equal to upward forces minus down, right? If you want to put those on your equation sheet, that's how I would write them to start. Okay, we're going to get another version of net force here in just a little bit, but this is the basic template that we use to solve for the net force when we've got multiple things going on. Okay, this would be for the x direction, and this would be for the y direction. Right, rightward minus leftward, and up minus down, right? Positives minus negatives. This is chapter 4, right? If you want to make a little separate category on your equation sheet, that's fine, but this is chapter 4. All right, so that's one way that we are able to calculate the net force. If we are given a lot of different forces, if we have to draw a diagram, this is the route that we will go. The alternate way to calculate the net force has to deal with Newton's second law, and it says an acceleration is directly proportional to the net force and inversely proportional to the mass, right? It gives this long, wordy definition, but really what Newton's second law comes down to is an equation, okay? And I'm going to rewrite this actually to say the net force of a system is equal to the mass times the acceleration of that system. Okay, so the net force, this is one that needs to go on your equation sheet. Net force is equal to the mass times the acceleration of a system. Okay, we know that the net force is the sum of all of our forces like we just talked about. And here's how the units break down, right? We talked about a Newton being kilograms times meters per second squared. Well, there's kilograms and meters per second squared, right? That's where those units come from. Mass times acceleration. Mass times acceleration is equal to the net force, which is measured in newtons. That's where all of that came from. Okay, so let me just show you something really quickly before we kind of get into too much more of it, right? If the net force can be calculated by taking the rightward forces minus the leftward forces, and we know F net is equal to mass times acceleration, we can say mass times acceleration is equal to the rightward forces minus the leftward, right? We're going to substitute MA in for the net force a lot. That's going to be something that we can do because if they both solve for the net force, we can set them equal to each other. Okay? This is going to be what we move into really tomorrow, but I want you to get a picture of what we're going to do with that. Okay? Today, our calculations, however, are much, much simpler. So today, we're just going to get information about the net force, where they give us information about the net force or they give us the other information that we need. So this one says, calculate the net force needed to accelerate a 1,000-kilogram car at 4.9 meters per second squared. So it asks us to solve for the net force. It gives us our mass. And it gives us our acceleration. So we don't even need to bother drawing a diagram. We don't need to bother leftward forces, rightward forces. We don't have to do any of that because it tells us our mass and our acceleration. So all I'm going to do is F net is equal to 1,000 times 4.9, right? And I get 4,900. And what would my units be if it is a force? It would just be newtons. Okay, pretty simple, right?